In this example problem, we're going to be finding a polynomial function of minimal degree that passes through the following 3 points. This is -1, 2, 1, 3, and 3, 5. It was a 2, and then I decided to edit it because, well, I do what I want. So first thing that should be pointed out is because we have a total of 3 points, that means we're going to want to set up something with 3 unknown constants, which is going to be a second degree polynomial. Now, the reason it's going to be a second degree polynomial is we're going to be setting up f of x is equal to, in order to get 3 constants out of this, we'll call it a0, a1, and a2 to represent the different powers of x that we'll see on each of these. So 0 for the a0 term, x to the first power for the a1 term, and x to the second power for the a2 term. So second degree polynomial. What we're going to do is plug these 3 points in so that we can solve for these unknown constants, a0, a1, and a2. So the interpretation that we can give to -1, 2 is that the y value will be 2 when the x value is -1. Now, putting this into more of a standard form, we'll call this a0 minus a1 plus a2 is equal to 2. That'll be the first row in our matrix once we set this up. For 1, 3, similar sort of concept. Y value will be 3 when the x value is 1. And again, rewriting this slightly, a0 plus a1 plus a2, that's going to be equal to 3. And then for the last one, that's 3, 5. Means that the y value is going to be 5 when we plug in x is equal to 3. So a0 plus 3a1 plus 9a2, that's going to be equal to 5. So what results is a system of 3 equations with 3 variables that we're going to be solving for. We'll set that up using a 3x4 augmented matrix. The first column will represent the constant a0, second one will be a1, third one will be a2, and then to the right of that we'll have what it's equal to. So interpretation of the first equation as the first row, coefficients are 1, -1, 1, 2. Second row, coefficients are 1, 1, 1, and it's equal to 3. And for the third equation, this would be 1, 3, 9, and it's equal to 5. Now what we're going to try to do here is put this into reduced row echelon form. So the very first thing I'm going to do is notice that I already have my lead 1 in the position where I want it, which is the 1, 1 entry. We're going to use this 1, 1 entry to zero out the 2 entries that are below it. We can do so by taking -1 times row 1, adding it to row 2, and having that become the new row 2, and do the same thing to row 3. -1 times the first row, add to the third row, that'll become the new third row. -1 times 1, oh sorry, I'm going to recopy the first row, since that is not changing. We'll take -1 times 1, add to 1, we'll get 0. -1 times -1, add to 1, we'll get 2. And -1 times 1, add to 1, we'll get 0. And that right there is an absolute gift. We're also doing -1 times 2, add to 3, and that's how we get this 1 here. Next up, -1 times 1, add to 1, we'll get 0. -1 times -1, add to 3, we'll get 4. -1 times 1, add to 9, we'll get 8. -1 times 2, add to 5, we will get 3. Now that we've zeroed out all of the other entries in the first column, we're going to sort of ignore the first column and ignore the first row and just worry about the second and third rows, treating this as its own little 2x3 augmented matrix. First thing I want is a 1 in the 2, 2 entry. I'm going to accomplish this by simply taking half of row 2 and calling that the new row 2. It will introduce a fraction. I'm not happy about that, but I'm pretty sure the fractions are going to be unavoidable on this one, so we might as well get used to it. First row remains the same, 1, -1, 1, augmented with 2. The second row will change. I'm going to take half of each of these entries, and that's going to give us 0, 1, 0, 1/2 for the 4 entries of that row. The third row remains unchanged. Now that we have our lead 1 in the 1, 1 entry, next thing to do is going to be to zero out the entries above and below it. So zeroing out what is above and below it to get reduced row echelon form, we're going to take row 2 added to row 1 to become the new row 1. We'll also take -4 times row 2, add to row 3, that'll become the new row 3. That'll use this lead 1 to zero out the entries above and below it. So, adding these together, 0 plus 1 will be 1. 1 plus -1 will be 0. 0 plus 1 will be 1. And 1/2 plus 2 will be 5/2. Second row remains unchanged. And taking -4 times the second row and adding to the third row, -4 times 0, add to 0 will remain 0. That's why we like those zeros there. -4 multiplied by 1, add to 4, we'll get the 0 that we desired. And then -4 multiplied by 0, add to 8, we'll get 8. -4 times 1/2 is -2, add to 3, we'll get 1. Now that we have lead 1s in the first and second row, we ignore the first and second row and focus on the third row. To get a lead 1 down there, we'll simply take 1/8 times row 3, and that'll become the new row 3. So first and second rows will remain the same. 1, 0, 1, 5/2. 0, 1, 0, 1/2. 0, 0, 1 will be 1/8. So we now have numerical answers for both A1 as well as A2. Let's finish this off by getting a 0 in the 1, 3 entry. We'll do that by taking -1 times row 3, add it to row 1, that'll become the new row 1. So third row remains the same. Second row remains the same. And then -1 times 0, add to 1 will be 1. -1 times 0, add to 0 will be 0. -1 times 1, add to 1, that'll be 0. -1/8, add to 5/2. 19/8, I think. There is, of course, a way to check all of this once we're done, and that's by actually plugging in the given points. So we can now interpret these 3 rows as being A0 is equal to 19/8, A1 is equal to 1/2, and A2 is equal to 1/8. We can interpret this as a polynomial in the following fashion. F of x is equal to the constant term A0, that's 19/8, plus A1 times x, so 1/2 times x, plus 1/8 times x squared. Now again, if you're interested in checking this answer, go all the way back to the original problem and verify that by plugging in the given points, we are getting the appropriate y values, or plugging in the appropriate x values, we'll get the associated y values. I'll leave that check to all of you.